factorial, parentheses x squared to the 2j plus 1. So this would be, fine, that's like the full series for it would be this. Now I can simplify that. So let's see here. When you multiply this laws of exponents, what's this give us? X to the what? We get 4j, right? Plus 2. But if I multiply this over there too, I get plus 2 plus 3, I get plus 5. Because I'm also taking into account the x cubed, right? And there it is. That's the Maclaurin series for that function. What if I just want the first 3 terms? Of course, what could we do? We could just use the general thing and plug in j equals 0, j equals 1, j equals 2, and see what pops out. Let me show you a different approach. First 3 terms, what I usually would do is just multiply. Sine of x squared is x squared minus 1/6 x squared cubed plus 1 over 5 factorial x squared to the 5th. Curses. And so what is that? Well, that's x to the 5th minus 1/6 x to the what? 6 plus 3 is 9. Here we've got 10 plus 3 is 13. 5 factorial happens to be 120. So there's the first 3 terms in the Maclaurin series for x cubed times the sine of x squared. Let's see if we can find it. Well, I mean, yes, but no. It's not what I want. So what I'm trying to show you guys is I've got some great pictures that illustrate to you the distinction between, say, the Taylor series and the function that we're approximating, all right? So you could, in principle, cover this in like first semester calculus, all right? I mean, but people don't usually do that. But you could. There's really nothing stopping you. Except, common human decency, that sort of thing. But, oh, come on. You guys got to stop me. No, not vines. My big fat fingers don't press these buttons right. All right, so if you think about what we're doing, like let's just stop back, take a step back and count the roses, What's the zeroth term is just saying the function's a constant. If you look at the first terms, what is this? If you look at f of a plus f prime of a times x minus a, what's that? That's the tangent line approximation to the function at a. Put a equals to c, it's what we did today. What if you go to the second order? Well, that's the best quadratic approximation to the function at the center c, right? And we just keep going, right? So the higher out you go, the higher order polynomial you're using to approximate the function. And so it's like beyond linearizations. It's quadratic approximations. It's the best cubic approximation. It's the best, kth order. So at the kth order, that's the am I going over? It's cracking me up. All right. Well, I guess we're out of time. I just want to show you this one. Then I'll open this up again some other day. We'll spend more time looking at it. But look at this, at least for today, since I got it out. The red dotted line. All right. The red dotted line is the sine function. This other family of curves, these are Taylor polynomials of various orders. So like the first Taylor polynomial to approximate sine we use in physics. Remember, sine of theta equals to theta? That's good to about 20 degrees. See? About 20 degrees, the blue line follows the red dotted line. If you want to get past 20 degrees, you got to use a higher order correction. The cube is the next thing. That's the purple one, I believe. As you can see, the cube follows it a little bit further out. Right? And then beyond that, here's a fifth order approximation, which, remember, the fifth order is positive? So it's like wait a minute, I'm probably wrong. I think that one's the cube. Cube is negative. So there's this is the cube. I'm an idiot. This is the third order. That's the seventh order. I think the purple one is the fifth order. The yellow one's the ninth order. But as you can see, as you get higher and higher Taylor polynomials, you follow the sine curve further and further. To get it all the way to infinity, you have to take it all the way to infinity in the sum. To be careful about these things, we have to understand what on earth convergence of a sum means. That's why we've been studying convergence. Anyway, I shut up. Thanks, guys. Oh, your homework. Turn in your homework.